Okay, I want to talk to you about the anesthesia machines, also known as anesthesia workstations. I think it's valuable to know a little bit about how these machines function because that should make you feel more comfortable interacting with this relatively complicated piece of equipment. So in this video, we'll talk about the basic functions of the anesthesia gas machine, which is to receive gas, whether that's oxygen, nitrous, air, or something else, control the flow of those gases, decreasing the pressure to safe levels, vaporizing some type of volatile gas to anesthetize the patient, and of course, delivering that gas to the patient. First, there will be inlets on the machine for oxygen, nitrous, air, or something else like heliox, nitric oxide, or other gases. Your main supply of gas to the anesthesia machine is from the primary pipeline. This is your wall oxygen or your wall air or whatever. It's delivered at a pressure of 50 psi straight from the wall. So you'll see these ports on the wall for any room that's equipped with a gas supply. These ports will have different diameter connections for each of the different gas. So that's called the diameter index safety system. Or DISS. These will be color-coded as well, but this prevents you from hooking up a nitrous line to an oxygen port because the diameter physically will not fit. Then you have your backup and portable gas supply from gas cylinders, which are full of highly pressurized gases. So your pressure here is very high because you're cramming all of this gas into a small cylinder. Instead of using a diameter index safety system here, they use these pins of different sizes. So these are pinholes actually on the head of this cylinder, and then this will be your gas outlet port. This is actually a pinhole. The actual pins are on the attachment piece for the head of this, which is called the yoke, and they'll have pins in a certain arrangement to attach onto this device with hose essentially connecting to the gas outlet. So if you tried to attach a hose with a yoke designed for an air cylinder to this oxygen cylinder, these pins would be in a different arrangement and you wouldn't be able to screw it into place. This is called the pin index safety system. For the gas cylinders, again, there's a color coding system, which is as follows here in the US and Canada and UK in brackets. The main difference being in the US, your oxygen is going to be green, your O2 lines are green, whereas they are white in Canada. Our E-cylinders are also still green though. We should talk a bit about the E-cylinders because it's useful for you to understand the pressure in these cylinders and sort of how long they'll last for a patient, and there are important differences between the O2 and nitrous cylinders, which we'll talk about. One very important difference between these tanks is the gas versus liquid status of them, and that's because of the critical temperature of each of these gases. So above a gas's critical temperature, it cannot be liquefied anymore. The critical temperature of oxygen is minus 118 degrees Celsius, which means that it cannot be liquefied at any naturally occurring temperature under any pressure on Earth. No liquid. Whereas the critical temperature of nitrous is 36.4 degrees Celsius, meaning that as long as you're below 36.4 degrees Celsius, which room temperature is, and many reasonable temperatures are, this can be liquefied by high pressures. So it can be liquid, and certainly is at high pressures that we have in our nitrous tanks. The volume of oxygen that fits into a full E-cylinder is 660 liters, and the pressure of that is going to be 1900 psi. Here is an oxygen tank, and it will only have oxygen in gas form in it, so no liquid in this tank. This full tank is going to be up to 1900 psi with 660 liters in it. Compare that to a nitrous tank, which will have a gas form above the liquid component of the tank. So its volume capacity is much higher than an oxygen tank. A full nitrous E-cylinder will be 1590. And these are the same physical size, but it just carries more gas because it can be compressed into a liquid. However, the pressure inside this tank, this 745 psi, is the saturated vapor pressure of this, meaning that it is the pressure that a gas form above a liquid in an enclosed container will exert on that container. You can also conceptualize this as the pressure that this gas will exert as it's trying to go from a liquid to a gas state. So when you measure the pressure coming off of this tank, it will be 745 psi. Even when you start using up, let's say your gas leaves here, when you start using up this liquid form, so it will turn into gas and drops the level, then all of this space will be gas. It's still going to be 745 psi because that's the pressure that the nitrous exerts in its gas form in this enclosed container. So even when you have your nitrous tank now only half full, you've used half of your potential gas from that tank, and you're left with 795 liters instead of 1590, but the pressure is still going to be read as 745 psi. Oxygen, on the other hand, since it's only in the gas form, the pressure in the tank is proportional to the leftover gas. So if you've used half of your O2 tank, you're left with 330 liters, and the pressure will be half of your original 1900 psi, so 950 psi. You can use this knowledge about the pressure in the O2 tank and its remaining volume to estimate the time remaining for the tank, or how long you can actually run the tank for before it will be empty, which is useful if you're transporting a patient and you need to know if you have enough oxygen to last for that transport. We said the volume is proportional to the pressure in the tank. So if we take our 660 liters divided by 1900 psi, we get 0.35 liters per psi. So if you want to know how many liters are remaining in your tank, that's just going to be that 0.35 times whatever psi the tank is reading. So let's just do a quick example. Say you have 700 psi on your O2 tank times 0.35 liters per psi will give you 245 liters. And then just simply divide how many liters are left in the tank by your liters per minute that you're running it at. And then you'll get how many minutes you can run this. So 245 liters divided by, let's say you are going at 15 liters per minute, which is what you would be doing an ambi-bag at. It'll give you 16 minutes with this O2 tank. Now, if you really want to quickly just know how many liters are left in your tank, essentially this is basically 1/3. So if you just divide the pressure in the tank by 3, you will get how many liters are remaining, and then simply just divide that by your liters per minute to tell you how many minutes are left in the tank. So I think the most clinically useful thing is just to look at your PSI, divide it by 3, and that'll tell you approximately how many liters are left in the tank. Of course, this only applies for your oxygen tank. If you want to know how much is left in your nitrous tank, you can't look at the pressure because it's going to be the same no matter how full your tank is until you're very close to empty. So you'd actually have to weigh this nitrous tank. and compare its weight to the full weight to tell how much of the liquid and gas nitrous is left in that tank.